Hello students, welcome to today's fascinating lesson where we will delve into the concept of conditional probability. This topic is not only fundamental to understanding probability theory but also plays a crucial role in various practical applications, from assessing risks to making informed decisions. The plan for today's lesson is as follows. Introduction and motivation. We will start by understanding why conditional probability is essential. We'll imagine a scenario where we need to determine the likelihood of one event happening given that another event has already occurred. This will set the stage for our exploration. Formal notation and definitions. Next, we'll introduce the special notation used for conditional probability, specifically the probability of event A occurring given that event B has occurred. We will understand how this notation helps in clearly communicating and solving problems involving conditional probabilities. Equation and applications. We will then explore the mathematical foundation of conditional probability, including the core formula. We will also learn how to rearrange this formula to derive the multiplication rule. This will unlock deeper insights, including an introduction to Bayes' theorem, which has vast applications ranging from criminal justice to machine learning. Special cases and independence. Finally, we will revisit the concept of independent events. We will see how the conditional probability formula simplifies when the events are independent, emphasizing the intuitive understanding that the probability of one event should not affect the probability of another if they are truly independent. By the end of this lesson, you'll be equipped with the tools to calculate and use conditional probabilities, setting a strong foundation for more advanced topics in probability and statistics. Let's embark on this mathematical journey together. To start, let's define some notation. Conditional probability is expressed as P, A given B, which reads as the probability of event A occurring given that event B has occurred. This notation is crucial because it helps us clearly understand and communicate the relationship between two events. The core formula for conditional probability is probability of A given B equals probability of A and B over the probability of B. This means that to find the probability of A happening, given that B has occurred, we divide the probability of both A and B occurring by the probability of B. For example, suppose we have two events. Event A, it rains, and event B, you take an umbrella. If we know the probability that it rains and you take an umbrella is P, A, and B, and the probability that you take an umbrella is PB, then we can calculate the conditional probability that it rains given you take an umbrella. Additionally, we can rearrange the formula to get the multiplication rule. Probability of A and B equals to the probability of A given B multiplied by the probability of B. This tells us that the probability of both A and B happening is the product of the probability of B happening and the probability of A happening given B. Now let's talk about independent events. Two events, A and B, are independent if the occurrence of one does not affect the occurrence of the other. Mathematically, events A and B are independent if probability of A given B equals to the probability of A. In other words, the probability of A occurring does not change whether B has occurred or not. For independent events, the multiplication rule simplifies to the probability of A and B equals to the probability of A multiplied by the probability of B. This formula can be very intuitive. If two events do not influence each other, the probability of both happening is just the product of their individual probabilities. Finally, a brief mention of Bayes' theorem, which extends conditional probability to more complex scenarios. Bayes' theorem states that the probability of A given B equals to the probability of B given A multiplied by the probability of A divided by the probability of B. This theorem allows us to update our beliefs about the probability of an event based on new information and has wide-ranging applications from diagnosing diseases to making predictions in machine learning. To summarize, we've learned the notation and definition of conditional probability, which is P, A given B. The core formula, which is the probability of A given B equal to the probability of A and B divided by the probability of B. The multiplication rule is the probability of A and B equals to the probability of A given B multiplied by the probability of B, and how these concepts simplify for independent events. With these tools, you are now equipped to tackle a variety of problems involving conditional probability. Let's dive into some examples to solidify our understanding of conditional probability. Suppose we have a deck of 52 cards. Event A is drawing a king and event B is drawing a card that is a heart. Let's find the probability of drawing a king given that the card is a heart using the conditional probability formula. Step 1. Identify the probability of A and B. There is one king of hearts in the deck. So the probability of having a king and heart is 1 over 52. Step 2. Identify the probability of B. There are 13 hearts in the deck. So the probability of heart is equal to 13 over 52. Finally, for step 3, apply the conditional probability formula. The probability of king given heart equals to the probability of king and heart divided by the probability of heart, which equals to 1 over 52 divided by 13 over 52, which equals to 1 over 13. So the probability of drawing a king given that the card is a heart is 1 over 13. Let's consider a scenario where 60% of students in a class have a laptop, which is represented by event L, and 40% have a tablet, which is represented by event T. Additionally, 25% of students have both a laptop and a tablet. We want to find the probability that a student has a tablet given that they have a laptop. Step 1. Identify the probability of L and T. This is given as 25% or 0.25. Step 2. Identify the probability of L. This is given as 60% or 0.6. Step 3. Apply the conditional probability formula. The probability of T given L equals to the probability of L and T divided by the probability of L, which equals tozero 0.25 divided by 0.6, which equals 25 over 60 or 5 over 12. So, the probability that a student has a tablet, given that they have a laptop, is 5/12. Now let's tackle a more challenging problem. Suppose there are 2 jars. Jar 1 contains 3 red balls and 2 blue balls. Jar 2 contains 4 red balls and 1 blue ball. You randomly pick a jar, then randomly pick a ball from that jar. What is the probability that the ball is red given that it came from jar 1? Step 1. Identify the probability of red in jar 1. From jar 1, the probability of picking a red ball is 3 over 5. The probability of picking jar 1 is a half. So the probability of red and jar 1 is 3/5 multiplied by a half, which equals to 3 over 10. Step 2. Identify the probability of jar 1. Since there are 2 jars to choose from, the probability of choosing jar 1 is a half. Step 3. Apply the conditional probability formula. The probability of red given jar 1 equals to the probability of red in jar 1 divided by the probability of jar 1. This equals to 3 over 10 divided by a half, which we can rearrange to 3 over 10 multiplied by 2 over 1, which equals to 3 over 5. So the probability that the ball is red, given that it came from jar 1, is 3/5. By working through these examples, you should now be confident with conditional probability. In today's lesson, we delved into the concept of conditional probability, an essential tool for understanding the likelihood of events given the occurrence of another event. We started by defining the notation PA vertical bar B, which represents the probability of event A occurring given that event B has occurred. We then introduced the core formula for conditional probability, which is the probability of A given B equals to the probability of A and B divided by the probability of B. This formula allows us to calculate the probability of a happening given B by dividing the probability of both A and B occurring by the probability of B. We also discussed the multiplication rule, which is the probability of A and B equals to the probability of A given B multiplied by the probability of B. This rule shows that the probability of both A and B occurring is the product of the probability of B and the conditional probability of A given B. We explored the concept of independent events, where the occurrence of one event does not affect the probability of the other. For independent events, the conditional probability, which is the probability of A given B, equals to the probability of A, and the multiplication rule simplifies too. The probability of A and B equals to the probability of A multiplied by the probability of B. In summary, we covered the notation and definition of conditional probability, the core formula and multiplication rule, the simplification for independent events, and an introduction to Bayes' theorem. With these concepts, you are now well equipped to analyze and solve problems involving conditional probability.